So first, I'd like to thank the organizers for giving me this wonderful opportunity to talk about our recent works on twisted Bilayer graphene. I'm Youngjoon Choi from Caltech, Nasberger Group. So twisted Bilayer graphene in real space creates Moiré pattern, and density of state is confined mostly on AA sites. And we roughly know how the band structure looks like. There are remote bands, flat band, and Dirac points at kappa points. And further calculations show that the orbitals from kappa points is localized mostly at AA site. On the other hand, orbitals at the gamma points is rather spatially distributed. So say the shape of the orbitals would look like these in space. So let's think about the simple consequence of the shape differences. Imagine we fill up 1 electron per Moiré, and they sit on AA sites. So if you try to add another electron from kappa point, it will cost more energy due to the Coulomb interaction compared to an electron from a gamma point. So there is a relative energy shift between kappa and gamma points due to this Coulomb interaction. And as previous speakers mentioned, this effect is predicted and captured in Hartree calculations in these theory papers. So relative shift between kappa and gamma points are visible as a function of doping. The more you fill up the band, the more you deform the band. But how do we verify it experimentally? So we've been measuring twisted Bilayer graphene with STM. This is the schematic of the device. And with our fabrication method, we got very nice topography. And we'd like to study this Hartree effect at slightly above the magic angle, which is a 1.32 degree. Because at the magic angle, we know that other interaction effects, such as flavor symmetry breaking and Fermi surface reconstruction, further complicate the band structure. So at 0 Tesla, we've observed 2 Van Hoff singularities crossing the Fermi energy in parallel without any modifications. When we apply a perpendicular magnetic field, we see Landau levels emerging from the flat band as well as remote bands. So let's name them, and the outer bands as gamma Landau levels because they appear outside of the band of singularity, and the inner one as kappa Landau level because it appears inside of the band of singularity, as schematically shown here. If they are really from gamma pockets and kappa points, and then as you increase the magnetic field, the gamma Landau level should move closer. And indeed, the gamma Landau level experimentally move closer with the magnetic field. And secondly, on an AA site, gamma Landau levels are missing, but on an AB site, they are more visible. On the other hand, kappa Landau level is visible on both AA and AB sites. So that is because gamma orbitals are spatially distributed and kappa orbitals are localized on AA site. So these two B field dependence and spatial dependence justify that central one is kappa point from the kappa point and the outer ones are from the gamma point. So having identified their origins, we now want to focus on their relative movements upon doping. So on the conduction band, the spacing between the 0th Landau level and the next Landau level changes with electron doping. On the valence side, the spacing is also changing, but in an opposite trend. So we measured how this spacing changes. So from -4 to +4 filling factors, it changes from 5 to 25 MeV for the valence band, and on the conduction band in an opposite way. This means that the band deforms significantly depending on the doping, and the conduction band and valence band deform in an opposite way. So we implemented this Hartree correction in our model and added a magnetic field this simulation result also captures this changing of the separation, and it nicely matches with the experiment. So another way to verify this band deformation is to check the angle dependence. So let's look at the shape of the conduction band. So at large angle, due to the Hartree effect, nu equals -2 is more curved than +2. And the gamma Landau level is away from the band of singularity. As we lower the angle, the bandwidth becomes narrower because we are approaching to the magic angle. And at +2, the band becomes very, very flat, and gamma Landau level merges with the band of singularity. However, at -2, the conduction band is not flat, and the gamma Landau level is still not merged with the band of singularity. And we need smaller angle to make them to merge. So depending on the doping, the angle where gamma Landau level and Van Hoff singularity merges changes. To visualize this angle effect, we measured an area where the angle varies from 1.3 to 1 degree continuously. So when the system is electron doped, at the top angle, gamma Landau level is very well separated from the Van Hoff singularity. And as we lower the twist angle, they come closer and closer, and finally meets around 1.1 degree. And at charge neutrality, they meet slightly higher. And when the system is Hall doped, gamma Landau level is very close to Van Hoff singularity from the beginning, and it merges around 1.2 degree. So this mapping demonstrates that depending on the doping, the merging angle changes due to the band deformation. And actually this merging of Landau level and Van Hoff singularity has a very important meaning. As you see it from these calculations, when the band becomes very flat, the density of state suddenly becomes very high. And experimentally, that's when the gamma Landau level merges with the Van Hoff singularity. So the point where they merge is the point where the density of state becomes very high. And as pointed in this paper, we can expect strong correlation effect starting to occur here. So let's look at the spectroscopy at 1.16 degree around the magic angle. With magnetic field, we still see these Landau levels and Van Hoff singularities. On the conduction band, the gamma Landau level and Van Hoff singularity comes closer, but they don't meet that Fermi energy. However, on the valence side, they just meet at the Fermi energy, and they somehow open a gap here. At 1.14, they obviously meet here on the valence side, and the gap is even deeper. But on the conduction side, gamma Landau level is still not merged with the Van Hoff singularity. We lower the angle, and finally the gamma Landau level merged with the Van Hoff singularity, and it created this gap. So actually these gaps are correlated Chern gaps that emerge when the density of state becomes very high and meets Stoner criterion at finite magnetic field. We discussed these topological phases in our previous works using a novel technique that enables STM to take a Landau Level Venn diagram, allowing us to compare it to transport measurements. For more details on the Chern phase, these Chern phases, please also see these papers. And since the correlated Chern phases are signatures of strong correlations, the band flattening gives rise to density of state increase, and it brings correlated physics at finite magnetic field. And it's not just that finite magnetic field. We can infer that the density of state increase due to the band flattening is also responsible for the correlated gaps at zero magnetic field. We measure density of state at the Fermi energy, which detects gaps as dark regions, and we vary the twist angle. Nu equals 0 and ±4 nicely shows low density of state due to the band gaps and Dirac points. We also see correlated gaps appearing exactly at -2, 1, 2, and 3 hidden factors. And because of their positions, we attribute them to the insulating states in transport. And moreover, -2 and +2 start to appear at different angles. -2 is higher than +2. And interestingly, they start to appear at the angles roughly where gamma Landau level merged with the Van Hook singularity in the previous slide. So we suspect that density of state increase due to the band flattening also plays a role here and creates correlated gaps at 0 Tesla. Finally, filling factors 1, 2, and 3, they also have some trend. They are connected to flavor symmetry breaking as seen in the spectroscopies, as well as compressibility measurement. And with our calculation, including Hartree Effect, we find that these polarized phases are favored below certain angles. And according to the calculation, nu equals 3 starts first, followed by 2 and 1, consistent with the observation. So I'd like to discuss on some of the discrepancies between theory and experiments. Experimentally, measured bandwidth is larger than 50 MeV, and we systematically studied that heterostrain in the device alone cannot account for this large bandwidth. And if we put rough value of Coulomb energy scale, then U over W is less than 0.5, might be small for the correlations. Also, we can measure Dirac velocity by Landau levels, and the Dirac velocity at 1.18 degree is turned out to be smaller than 1.04 degree, which is very strange because we see a strong correlation at 1.04, and at 1.18 we basically the correlation is nearly absent. So we think that the whole band does not need to be flat. Instead, only a part is sufficient for correlation. And Dirac velocity, for example, in this calculation is not changing that much, so it is probably not relevant. Our calculation also shows that the interaction-driven band flattening enhances the magic angle range. If we assume that the threshold density of states for correlation is probably this much, then in non-interacting model, we expect correlation happening only in this narrow range, but including interaction results in a much wider angle range, which agrees with experiment. So our conclusion is that the interaction-driven band flattening enhances density of state and determines the onset of correlations. We know that once flavor symmetry breaking happens, it further complicates the band structure. So it is interesting direction to include flavor symmetry breaking within this context and try to match with the observations. And finally, you want to say something on this similar gap structure that earlier today Kevin mentioned from Princeton University. So we also see this gap structure between filling factor -2 and -3. And in our case, the gap is a little bit more asymmetric, but it definitely dies away with the temperature, and completely dies away around 5 Kelvin. So this could be some signatures of superconductivity or some kind of pseudogap phase developed here. For more details, please check our paper. So I'd like to thank Hyunjin, who performed these measurements together, my theory collaborators, and Stefan, who's leading the group. And thank you for your attention.